Good day. Mahir and together with my partner Angela are here to talk about one of the topics in Louis Frenzel's book, Principle of Electronic Communication Systems, and this topic is known as antennas and wave propagation.
Under this chapter, we have three subtopics, namely antenna fundamentals, common antenna types, and radio wave propagation. In wireless communication systems, an RF signal generated by a transmitter is sent into free space and eventually picked up by a receiver. The interface between the transmitter and free space and between free space and the receiver is the antenna. The incredible variety of antenna types used in radio communication are all based on a few key concepts. This chapter introduces all the most popular and widely used antennas in HF, VHF, and UHF applications.
Also discussed are the characteristics of free space and its ability to propagate signals over long distances. A study of wave propagation, how radio signals are affected by the Earth and space in moving from transmitting antenna to receiving antenna, is critical to understanding how to ensure reliable communication over the desired distance at specific frequencies. Let us now proceed to the discussion of the first subtopic, antenna fundamentals.
The interface between the transmitter and free space and between free space and the receiver is the antenna. In layman's term, an antenna is an electrical device which converts electric power into radio waves and vice versa.
We can usually see them on radios and television. At the transmitting end, the antenna converts the transmitter RF power into electromagnetic signals. At the receiving end, the antenna picks up the electromagnetic signals and converts them into signals for the receiver. Radio waves are a type of electromagnetic radiation with wavelengths in the electromagnetic spectrum longer than infrared light. Radio waves have frequencies from 3 terahertz to as low as 3 kilohertz and corresponding wavelengths ranging from 100 micrometers to 100 kilometers.
Radio waves travel at a speed of 186,000 miles per second or 162,000 nanomiles per second. Knowing the speed of radio waves permits the distance or a remote target to be determined. A magnetic field is the magnetic effect of electric current and magnetic materials. The magnetic field at any given point is specified by both a direction and a magnitude. As such, it is a vector field.
Magnetic fields can be produced by moving electrical charges and the intrinsic magnetic moments of elementary particles associated with a fundamental quantum property, their spin. The SI unit for magnetic field strength is ampere turns per meter.
This figure shows a magnetic field around a current-carrying conductor. Although the magnetic field is a continuous force field, for calculation and measurement purposes, it is represented as individual lines of force. This is how the magnetic field appears in most antennas.
The strength and direction of the magnetic field depend upon the magnitude and direction of the current flow. The strength of a magnetic field H produced by a wire antenna is expressed by H equals 1 over 2 pi d, where I equals the current and has the units ampere, d equals the distance from wire with the unit m or meters. The SI unit for the magnetic field strength is ampere turns per meter. Electric field is defined as the electric force per unit charge. The direction of the field is taken to be the direction of the force it would exert on a positive test charge. The electric field is radially outward from a positive charge and radially in toward a negative point charge.
The SI unit for electric field strength is volts per meter. Permittivity is the dielectric constant of the material between two conductors. A common example in electronics is the electric field produced between the plates of a charge capacitor, which is shown in the figure. An electric field exists between any 2 points across which a potential difference exists.
The strength of an electric field E is expressed by E equals Q over 4 pi epsilon d squared, where Q was a charge between between the 2 points with the unit C. Epsilon equals permittivity. D equals distance between conductors with the unit M. The SI unit for electric field strength is volts per meter. Permittivity is the dielectric constant of the material between the two conductors. The dielectric is usually air of free space, which has an epsilon value or approximately 8.85 times 10 to the 12 epsilon times r, where epsilon times r is the electric constant of the medium.
At any given time in a two-wire transmission line, the wires have opposite polarities. During one half cycle of the AC input, one wire is positive and the other is negative. During the negative half cycle, the polarity reverses. The direction of the electric field between the wires reverses once per cycle. The direction of current flow in one wire is always opposite that in the other wire, therefore, the magnetic field combined.
A transmission line is made up of a conductor or conductors. Transmission lines do not radiate signals efficiently. The closeness of the conductors keeps the electric field concentrated in the transmission line dielectric. The magnetic fields most cancel one another. The electric and magnetic fields do extend outward from the transmission line, but the small amount of radiation that does occur is extremely inefficient.
The first figure shows the electric and magnetic fields around a two-wire transmission line. Note that at any given time, the wires have opposite polarities. During one half cycle of the AC input, one wire is positive and the other is negative. During the negative half cycle, the polarity reverses.
This means that the direction of the electric field between the wires reverses once per cycle. The second figure is a detail of an electric field around conductors. Note also that the direction of current flow in one wire is always opposite than in the other wire. Therefore, the magnetic fields combine as shown in the third figure.
If a parallel wire transmission line is left open, the electric and magnetic fields escape from the end of the line and radiate into space.
The next information is the explanation of the figures that will be shown later on. The electric field spreads out from conductor to conductor. Optimum radiation occurs if the segment of transmission wire converted into an antenna is 1/4 wavelength long at the operating frequency.
The radiation in the first figure is inefficient and unsuitable for reliable transmission or reception.
In the second figure, the radiation from a transmission line can be greatly improved by bending the transmission line conductors so they are at the right angle to the transmission line. The magnetic fields no longer cancel, they now aid one another.
The wave impedance of an electromagnetic wave is the ratio of the transverse components of the electric and magnetic fields.
Antennas produce two sets of fields, the near field and the far field. The near field and far field are regions of the electromagnetic field around an object, such as transmitting antenna or the result of radiation scattering of an object.
Polarization refers to the orientation of magnetic and electric fields with respect to the Earth. If an electric field is parallel to the Earth, the electromagnetic wave is said to be horizontally polarized. If the electric field is perpendicular to the Earth, the wave is vertically polarized. Antennas that are horizontal to the Earth produce horizontal polarization, and antennas that are vertical to the Earth produce vertical polarization. Reciprocity is one of the most useful property of antennas. Reciprocity states that the receive and transmit properties of an antenna are identical. Hence, antennas do not have distinct transmit and receive radiation patterns.
A transmitting antenna takes a voltage from the transmitter and converts it into an electromagnetic signal. A receiving antenna has a voltage induced into it by the electromagnetic signal that passes across it.
An antenna can be a length of wire, a metal rod, or a piece of tubing. Antennas radiate most effectively when their length is directly related to the wavelength of the transmitted signal.
Most antennas have a length that is some fraction of a wavelength. One half and one quarter wavelengths are most common. In radio and telecommunications, a dipole antenna or doublet is the simplest and most widely used class of antenna. It consists of two identical conductive elements such as metal wires or rods, which are usually bilaterally symmetrical. The driving current from the transmitter is applied, or for receiving antennas, the output signal to the receiver is taken between the two halves of the antenna.
Each of the two rod elements is approximately one-fourth wavelength long, so the whole antenna is a half wavelength long. The radiation pattern of a vertical dipole is omnidirectional. It radiates equal power in all azimuthal directions perpendicular to the axis of the antenna.
The halfway dipole is one of the most widely used antenna types, is shown in the figure. The transmission line is connected at the center. The dipole has an impedance of 73 volts at its center, which is the radiation resistance. At the resonant frequency, the antenna appears to be pure resistance of 73 volts.
An antenna is a frequency-sensitive device. To get a dipole to resonate at the frequency of operation, the physical length must be shorter than the one-half wavelength computed by lambda equal to 492 per f. Actual length is related to the ratio of length to diameter, conductor shape, Q, the dielectric, and the condition known as the end effect.
The end effect of an antenna is an effective capacitance which makes a dipole antenna effectively slightly longer. A half-wave resonant dipole is going to be slightly less than a half wavelength in free space. If the wire were infinitely thin, there would be no end effect, but the two halves of a dipole act like small capacitors across the feed point.
The bandwidth of an antenna is determined by the frequency of operation and the Q of the antenna according to the relationship BW, which is equal to FR over Q. Although it is difficult to calculate the exact Q for an antenna, as the above relationship shows, the higher the Q, the narrower the bandwidth. Lowering Q widens bandwidth in resonant circuits as high Q is undesirable because it makes the circuit more selective. For an antenna, low Q and hence wider bandwidth is desirable so that the antenna can operate over a wide range of frequencies with reasonable SWR.
As a rule of thumb, any SWR before 2.1 is considered good in practical antenna work. Modern communication transceivers rarely operate at just one frequency. Typically, they operate on a selected channel inside a broader band of frequencies. Furthermore, the transmitter is modulated, so there are sidebands. If the antenna has too high a Q and its bandwidth is too narrow, the SWR will be higher than 2.1 and sideband clipping can occur.
The Q and thus the bandwidth of an antenna are determined primarily by the ratio of the length of the conductor to the diameter of the conductor. When thin wire is used as the conductor, the ratio is very high, usually in the 10,000 to 30,000 range, resulting in high Q and narrow bandwidth. A length to diameter ratio of 25,000 results in a Q of about 14.
A common way to increase bandwidth is to use a version of the dipole antenna known as the conical antenna. The primary advantage of conical antennas is their tremendous bandwidth. The first figure in the next slides shows a conical antenna.
Cones are difficult to make and expensive, and a popular and equally effective variation of the conical antenna is the bow tie antenna. A two-dimensional cone is a triangle, therefore a flat version of the conical antenna looks like two triangles, or a bow tie. One bow tie version of the conical antenna shown in the second figure would have the same shape and dimensions, but it would be made of flat aluminum.
Bowtie antennas can also be made of a grillwork of conductors instead of a flat plate, as shown in the third figure. This configuration reduces wind resistance. If the spacing between the conductors is made less than 0.1 in wavelength at the highest operating frequency, the antenna appears to be a solid conductor to the transmitter or receiver.
Dipole polarization is a polarization arising from the orientation of molecules which have permanent dipole moments arising from an asymmetric change distribution. It is also known as orientation polarization.
A dipole antenna can be mounted either vertically or horizontally. Horizontal mounting is preferred at the lower frequencies because the physical construction, mounting, and support are easier. This type of mounting also makes it easier to attach the transmission line and route it then to the transmitter or receiver, while vertical mounting is common at the higher frequencies where the antennas are shorter and made of self-supporting tubing.
The radiation pattern of any antenna is the shape of the electromagnetic energy radiated from or received by the antenna. A bare dipole is not considered a directional antenna. However, like all antennas, its radiation is not uniform in all directions. Its radiation pattern in three dimensions is shaped like a toroid, symmetric about the axis of the dipole. The radiation is maximum at right angles to the dipole, dropping off to zero on the antenna's axis. Therefore, a dipole mounted vertically will be omnidirectional in the horizontal plane with a modest gain, at the expense of radiation in the vertical direction.
In a radio antenna pattern, the half-power beam width is the angle between the half-power points of the main lobe. When referenced to the peak effective radiated power of the main lobe, the measure of an antenna's directivity is beam width, the angle of the radiation pattern over which a transmitter's energy is directed or received. Beam width is usually but not always expressed in degrees and for horizontal plane.
The radiation pattern of half-wave dipole has the shape of a donut, as shown in the figure. It shows the pattern with one half the donut cut away. The dipole is at the center hole of the donut, and the donut itself represents the radiated energy. To an observer looking down on the top of the dipole, the radiation pattern would appear to be a figure 8.
Gain is defined as the output of an electronic circuit or device divided by the input. Obviously, passive devices such as antennas cannot have gain in this sense. The power radiated by an antenna can never be greater than the input power. However, a directional antenna can radiate more power in a given direction than a non-directional antenna. And in this favored direction, it acts as if it had gain. Antenna gain of this type is expressed as the ratio of the effective radiated output power P out to the input power P in.
Effective radiated power is the actual power that would have to be radiated by a reference antenna to produce the same signal strength at the receiver as the actual antenna produces. Antenna gain is dB equals 10 log P out over P in, usually expressed in decibels.
The power radiated by an antenna with directivity and therefore gain is called effective radiated power or ERP. The ERP is calculated by multiplying the transmitter power feed to the antenna P sub T by the power gain AP of the antenna. ERP equals A sub P times P sub T.
A folded dipole is a dipole antenna with the ends folded back around and connected to each other, forming a loop. Because the folded dipole forms a closed loop, one might expect the input impedance to depend on the input impedance of a short-circuit transmission line. Also, because the folded dipole is folded back on itself, the currents can reinforce each other instead of canceling each other out. So the input impedance will also depend on the impedance of the dipole antenna.
The following figure showed the dipole's basic configuration and construction with twin lead. The basic configuration has a 300 ohm impedance that is not present in the construction with twin lead. On the other hand, the construction with twin lead has twisted and soldered wires, which is replaced by spacing in the basic configuration.
A Marconi antenna is a class of radio antenna consisting of a straight rod-shaped conductor often mounted perpendicularly over some type of conductive surface called a ground plane. The driving signal from the transmitter is applied, or for receiving antennas, the output signal to the receiver is taken between the lower end of the monopole and the ground plane. One side of the antenna feed line is attached to the lower end of the monopole, and the other side is attached to the ground plane, which is often the earth. This contrasts with a dipole antenna, which consists of two identical rod conductors, with the signal from the transmitter applied between the two halves of the antenna.
The monopole is a resonant antenna. The rod functions as an open resonator for radio waves, oscillating with standing waves, voltage, and current along its length. Therefore, the length of the antenna is determined by the wavelength of the radio waves it is used with. The most common or fundamental form is the quarter wave monopole, in which the antenna is approximately one-fourth of the wavelength of the radio waves. The monopole antenna was invented in 1895 by radio pioneer Guglielmo Marconi. For this reason, it is sometimes called antenna. Common types of monopole antenna are the whip, rubber ducky, helical, random wire umbrella, inverted L and T antenna, inverted F, mass radiator, and the ground plane antennas.
Like a dipole antenna, a monopole has an omnidirectional radiation pattern. That is, it radiates equal power in all azimuthal directions, perpendicular to the antenna, but the radiated power varies with elevation angle, with the radiation dropping off to zero at the zenith of on the antenna axis. It radiates vertically polarized radio waves.
The figures on this slide shows two types of ground plane antennas. The first one shows one-quarter wavelength vertical antenna, while the second one shows the use of radials as a ground plane. Vertical polarization and omnidirectional characteristics can also be achieved by using a one-quarter wavelength vertical radiator as shown in the first figure.
If a good electrical connection cannot be made to the earth, then an artificial ground plane can be constructed of several one-quarter wavelength wires laid horizontally on the ground or buried in the earth, as seen on the second figure.
When a good electrical connection to the earth has been made, the earth becomes what is known as a ground plane. If a ground plane cannot be made to the Earth, an artificial ground can be constructed of several one-quarter wavelength wires laid horizontally on the ground or buried in the earth.
These horizontal wires at the base of the antenna are called radials, and the collection of radials is called a counterpoise.
In addition to its vertical polarization and omnidirectional characteristics, another major benefit of the one-quarter wavelength vertical antenna is its length. It is one-half the length of a standard dipole, which represents a significant savings at lower radio frequencies. Additionally, they provide an equal amount of radiation in all directions, which is usually ideal for broadcasting.
For many applications, for example, with portable or mobile equipment, it is not possible to make the antenna a full one-quarter wavelength long. To overcome this problem, much shorter antennas are used and lumped electrical components are added to compensate for the shortening. When a vertical antenna is made less than one-quarter wavelength, the practical effect is a decreased inductance. The antenna no longer resonates at a desired operating frequency, but at a higher frequency. To compensate for this, a series inductor called a loading coil is connected in series with the antenna coil, as shown in the figure. The loading coil brings the antenna back into resonance at the desired frequency. The coil is sometimes mounted external to the equipment at the base of the antenna so that it can radiate along the vertical rod. The coil can also be contained inside the handheld unit as in the cordless telephone.
Directivity refers to an antenna's ability to send or receive signals over a narrow horizontal directional range.
Directivity is a figure of merit, usually for an antenna. It measures the power density and the antenna radiates in the direction of its strongest emission versus the power density radiated by an ideal isotropic radiator, radiating the same total power.
A highly directional antenna acts as a type of filter to provide selectivity. Directional antennas provide greater efficiency of power transmission. Directivity, because it focuses the power, causes the antenna to exhibit gain, which is one form of amplification.
Antennas can also be designed to be unidirectional. Unidirectional antennas send or receive signals in one direction only. In the first figure, it shows the directivity pattern of a highly directional antenna. The larger loop represents the main response curve for the antenna. Maximum radiation or reception is in the direction of 0 degree. The three smaller patterns or loops going off in different directions from the main larger pattern are also called minor lobes. A three-dimensional version of the horizontal radiation pattern shown in the first figure is given in the second figure.
An antenna array is a set of individual antennas used for transmitting and receiving radio waves, connected together in such a way that their individual currents are in a specified amplitude and phase relationship. The interactions of the different phases enhances the signal in one desired direction at the expense of other directions. This allows the array to act as a single antenna, generally with improved directional characteristics than would be obtained from the individual elements.
A parasitic array consists of a basic antenna connected to a transmission line, plus one or more additional conductors that are not connected to the transmission line. These extra conductors are referred to as parasitic elements, and the antenna itself is referred to as the driven element.
A Yagi antenna is made up of a driven element and one or more parasitic elements. Three-element Yagi antenna shown in the figure has a gain of about 8 decibels when compared to a half-wave dipole. The simplest Yagi is a driven element and a reflector with a gain of about 3 decibels over a dipole. Most Yagis have a driven element, a reflector, and from 1 to 20 directors. The greater the number of directors, the higher the gain and narrower the beam angle.
A driven array implies that all of the elements have an electrical connection to the transmitter or receiver through circuitry that tailors their respective currents to the same end. One common example is the log period dipole array frequently used as a rooftop TV antenna. Driven arrays in which all the radiating elements are connected to the energy source have smaller losses than parasitic arrays.
Driven arrays often, but not always, consist of elements which are identical. Frequently, these are just half-wave dipole or quarter-wave monopole vertical elements. The resulting array inherits the characteristics of that basic element, but the resulting array behavior is determined more by the geometrical arrangement of the elements and the phases, and sometimes amplitudes, which each is assigned.
The three basic types of driven arrays are the collinear, the broadside, and the endfire. A fourth type is the wide bandwidth log periodic antenna.
A collinear antenna, also called collinear or collinear antenna array, is a set of dipole antennas aligned along their length so they form one long line. Each element of the dipole antennas is one half wavelength long. Properly aligned and phased, a collinear array can provide a 3 decibel or more increase in signal strength. A 3 decibel increase in signal strength is about equal to doubling the signal strength. This increase in signal strength occurs perpendicular to the length of the array, so the arrays are usually mounted vertically to increase the signal strength in the horizontal plane.
Collinear arrays usually have a maximum of four elements as a result of problems with trying to keep six or more elements in phase. A four-element collinear antenna consists of two separate antennas, each with two elements and each element one-half wavelength long, and mounted vertically so all the elements are in line. They are connected using a coaxial cable cut to be one-half wavelength long. Calculated using the velocity factor of the cable, it is this coaxial cable that keeps the elements of the antenna in phase.
This figure shows the radiation pattern of a four-element collinear antenna.
A broadside array is a stacked collinear antenna consisting of half-wave dipoles spaced from one another by one-half wavelengths. It has its intended directionality at right angles to the array direction.
The figure shows a broadside array. The broadside antenna is bidirectional in radiation, but the radiation pattern has a very narrow beam width and high gain. This antenna produces a highly directional radiation pattern that is broadside or perpendicular to the plane of the array.
The end fire array uses two half-wave dipoles spaced one-half wavelength apart. It is one in which the intended directionality is in the direction of the array.
The figure shows an end-fire array. The end-fire array has a bidirectional radiational pattern, but with narrower beam widths and lower gain. The radiation is in the plane of the driven elements. A highly unidirectional antenna can be created by careful selection of the optimal number of elements with the appropriately related spacing.
A log periodic antenna, or LP, is also known as a log periodic array or log periodic aerial, is a multi-element directional antenna designed to operate over a wide band of frequencies. It was invented by Dwight Isabel and Raymond Duhamel at the University of Illinois in 1958.
This figure shows a log periodic antenna. The lengths of the driven elements vary from long to short and are related logarithmically. The spacing is also variable.
Impedance matching is the practice of designing the input impedance of an electrical load or the output impedance of its corresponding signal source to maximize the power transfer or minimize signal reflection from the load. A Q-section or matching stub is a 1/4 wavelength of coaxial or balanced transmission line of a specific impedance that is connected between a load and a source and is used to match impedances.
A balun is a transformer used to match impedances. An antenna tuner is a variable inductor, one or more variable capacitors, or a combination of these components connected in various configurations.
This figure shows a 1/4 wavelength matching stub or Q section.
This figure shows a 4-1 balun made with bifilar windings on a toroid core. Bifilar windings, in which two parallel wires are wound together as one around the core, provide maximum coupling between wires and core. The connections of the wires are such as to provide a balanced to unbalanced transformation.
A common example of such a balun is one that provides a 75 volts unbalanced impedance one on one end and a 300 volts balanced impedance on the other. Baluns are fully bidirectional. For example, either end can be used as the input or the output. Such baluns have excellent broadband capabilities and work over a very wide frequency range.
When balance and matching sections cannot do the job, antennas, antenna tuners are used. An antenna tuner is a variable inductor, one or more variable capacitors, or a combination of these components connected in various configurations. L, T, and pi networks are all widely used. The inductor and capacitor values are adjusted until the SWR indicates that the impedances match.
One popular variation of the antenna tuner is a transmatch circuit which uses a coil and three capacitors to tune the antenna for optimal SWR, which is shown in this figure. Capac- Capacitors C2 and C3 are ganged together and tuned simultaneously.
Radio propagation is the behavior of radio waves when they are transmitted or propagated from one point on the Earth to another, or in various parts of the atmosphere. Radio propagation is affected by the daily changes of water vapor in the troposphere and ionization in the upper atmosphere due to the sun.
Understanding the effects of varying conditions on radio propagation has many practical applications, from choosing frequencies for international shortwave broadcasters to designing reliable mobile telephone systems to radio navigation to operation of radar systems.
As a form of electromagnetic radiation, like light waves, radio waves are affected by the phenomena of reflection, refraction, diffraction, absorption, polarization, and scattering.
Reflect means to cast or turn back, and reflection is the act of reflecting. Electromagnetic reflection occurs when an incident wave strikes a boundary of two media or conductive medium such as metal surface or earth surface, and some or all of the incident power does not enter the second material or medium. The waves that do not penetrate the second medium are reflected.
Radio wave reflection follows the principles of light wave reflection. That is, the angle of reflection is equal to the angle of incidence, as shown in the figure. The radio wave is shown as a wavefront. To simplify the drawing, only the electrical lines of force, designed by arrows, are shown. The angle of incidence is the angle between the incoming line of the wave and a perpendicular line to the reflecting surface. The angle of reflection is the angle between the reflected wave and the perpendicular line. The figure shows the direction of the electric field approaching the reflecting surface is reversed from that leaving the surface. The reflection process reverses the polarity of a wave. This is equivalent to a 180-degree phase shift.
Refraction occurs when waves pass from one density medium to another with different velocities of propagation. The amount of bending or refraction that occurs at the interface of two materials of different densities is quite predictable and depends on the refractive index, which is simply the ratio of the velocity of propagation in a given material.
The relationship between the angles and the indices of refraction is given by a formula known as Snell's law. N1 sine theta 1 equals N2 sine theta 2, where N1 is the index of refraction of initial medium, N2 is the index of refraction of medium into which wave passes, theta 1 is the angle of incidence, and theta 2 is the angle of refraction.
The figure shows how a wave is refracted. The incident wave from a transmitter travels through air where it meets a region of ionized air that causes the speed of propagation to slow. The incident wave has the angle of theta 1 to a perpendicular to the boundary line between air and ionized air. The bent wave passes through the ionized air. It now takes a different direction, however, which has an angle of theta 2 with respect to the perpendicular.
Diffraction is defined as the modulation or redistribution of energy within a wave front when it passes near the edge of an opaque object. This effect is the result of Huygens' principle, advanced by the Dutch astronomer Christian Huygens in 1690. The principle states that each input on a spherical wavefront
Remember that the light and radio waves travel in a straight line. If an obstacle appears between a transmitter and receiver, some of the signal is blocked, creating what is known as a shadow zone, which is shown in the first figure.
as the wavefront passes the object, the point sources of waves at the edge of the obstacle create additional spherical waves that penetrate and fill in the shadow zone. This phenomenon, sometimes called knife-edge diffraction, is illustrated in the second figure.
The three basic paths that a radio signal can take through space are ground wave, sky wave, and space wave.
Ground wave propagation is a method of radio frequency propagation that uses the area between the surface of the Earth and the ionosphere for transmission. The ground wave can propagate a considerable distance over the Earth's surface, particularly in the low frequency and medium frequency portion of the radio spectrum. Ground wave radio propagation is used to provide relatively local radio communications coverage.
As shown in the figure, ground or surface waves leave an antenna and remain close to the Earth. Ground waves actually follow the curvature of the Earth and can therefore travel at distances beyond the horizon. Ground waves are the main signal path for radio signals in the 30 kHz to 3 MHz range. The signals can propagate for hundreds and sometimes thousands of miles at these low frequencies.
In radio communication, skywire or skip refers to the propagation of radio waves reflected or refracted back toward Earth from the ionosphere, an electrically charged layer of the upper atmosphere. Since it is not limited by the curvature of the Earth, skywave propagation can be used to communicate between the horizon at intercontinental distances. It is mostly used in the long wave frequency bands.
In this figure, the bending of the signal is caused by refraction in the region of the upper atmosphere, known as the ionosphere. Ultraviolet radiation from the sun causes the upper atmosphere to ionize, for example, to become electrically charged.
The radio waves having high frequencies are basically called as space waves. These waves have the ability to propagate through atmosphere, from transmitter antenna to receiver antenna. These waves can travel directly or can travel after reflecting from Earth's surface to the troposphere surface of Earth.
The figure shown explains that because of the space wave's straight line nature, direct wave signals travel horizontally from the transmitting antenna until they reach the horizon, at which point they are blocked. If a direct wave signal is to be received beyond the horizon, the receiving must be high enough to intercept it.
The formula for computing the distance between a transmitting antenna and the horizon is d equals the square root of 2h sub t, where h sub t is the height of the transmitting antenna. Its unit is in feet. D is the distance from transmitter to horizon, which is expressed in miles. This is called the radio horizon. A radio repeater or repeater stations is a combination of a radio receiver and a radio transmitter that receives a weak or low level signal and retransmits it at a higher level or higher power, so that the signal can cover longer distances without degradation. This article refers to professional, commercial, and government radio systems.
A trunked radio system is a complex type of computer-controlled two-way radio system that allows sharing of relatively few radio frequency channels among a large group of users. Communication satellites act as fixed repeater stations. The receiver-transmitter combination within the satellite is known as a transponder.
Fading is the variation in signal amplitude at the receiver caused by the characteristics of the signal path and changes in it. Fading typically makes the receiver signal smaller. Fading is caused by four factors: variation in distance between transmitter and receiver, changes in the environmental characteristics of the signal path, the presence of multiple signal paths, relative motion between transmitter and receiver.
A diversity system uses multiple transmitters, receivers, or antennas to mitigate the problems caused by multi-path signals. Two common types of diversity are frequency and signal spatials. With frequency diversity, the theory is that signals on different frequencies will react differently to the various fading mechanisms, thereby resulting in at least one reliably received signal. To be effective, the frequencies should be widely spaced from one another.
Another more widely used form of diversity is called space or spatial diversity. Diversity systems are used mainly at base stations rather than in portable or handheld units. The basic idea is that antennas at slightly different locations will receive different variations of the signals, with one being better than another. The spacing may be horizontal or vertical, whichever is the more convenient. However, in some cases, one arrangement will be superior to the other.
And that covers up our discussion. Thank you for spending your time with us. Have a nice day ahead.